So this is kind of a broad question, and I'll apply it to a specific problem in a moment. But the idea is that we want to use Green's theorem to determine the area of this region. So R is just a general region. Now notice that the area of a region is just given by the double integral over the region of the function 1 dA. Okay, so how can we connect this to Green's theorem? Well, remember, Green's theorem lets us connect, or not lets us connect, but Green's theorem connects certain integrals over a region to certain integrals over the boundary of that region. So in particular, if one, so let me redo this. So if we see this as being the partial derivative of q with respect to x minus the partial derivative of p with respect to y, where p and q are the components of some vector field pq, then the area is equal to the line integral over the boundary of R. And now notice that the boundary of R is a closed curve, so we're going to put the loop there and say it has counterclockwise orientation of the vector field f dotted with ds. Okay, that's what Green's theorem says. Now this is if one satisfies this equation here. In other words, is there a vector field f that satisfies this equation? And so basically what this asks us, can we find two functions, q and p, such that the partial derivative of q with respect to x minus the partial derivative of p with respect to y is equal to 1. Okay, so let's think about this. Maybe the first guess would be, what if I choose q of xy to be equal to x and p of xy to be equal to y? Then qx minus py, then that's going to be equal to 0. So that's not going to quite work. So what about if we make this minus y? Then the x derivative of q is 1, the y derivative of p is minus 1, and so we get 1 minus 1, so that's 2. So that doesn't quite work either, but if we divide both sides of these by 2, then we get something that works. Okay, so if the vector field is f is equal to minus y over 2, x over 2, if this is the vector field, then the line integral of f around the boundary of R is going to be equal to the area of that region. So this is actually a pretty useful piece of information to have. So let me give you one example. So there is an instrument called a planimeter, I guess that's how you say this, and it is a tool that you can use to compute the area of an arbitrary two-dimensional shape. And essentially what it does, let me see if I can get a view here. Essentially what's going on is you slide it around the boundary of your region, and it basically does a line integral of a certain vector field around the region, and using Green's theorem, it uses that to compute the area of that region. This is the Wikipedia article right here. This is Green's theorem right here in the center here. That's exactly what Green's theorem says. Anyways, so this is a pretty practical thing to use. But for this class, we're just going to use it to compute the area of a circle. So that's what we are asked to do in the problem. So let's go on ahead and do that. So let me get back up there. So in particular, the particular problem I'm looking at, your version might be a little bit different. It says use Green's theorem. Sorry, let me use a different color. It says use Green's theorem to find the area of a circle of radius 9 centered at the origin. Of course, we know the answer should be 81 pi, so it's nice to be able to already know the answer, then we'll see if our method sort of is consistent, which mathematically we know it should be. I mean, we've seen the proofs. Well, we haven't seen the proofs in this class, but the proofs exist. You probably trust it. But I always like doing stuff like this because it shows that it just shows it works. It sort of makes it come alive in as much as math can come alive. Okay, so we want to do the integral of the vector field. So C, this is the boundary of a circle of radius 9, centered at the origin, and we want to integrate the vector field minus y over 2 x over 2 ds. So remember, the first step here is to come up with a parameterization. So r of t is equal to 9 cosine t, 9 sine t, 0 less than or equal to t less than or equal to 2 pi. And observe, this does give the counterclockwise parameterization, so we're okay there. And now we'll use this. This is equal to the integral from 0 to 2 pi. So this is going to be minus 9 sine t over 2, comma, 9 wow, I'm having trouble writing, 9 cosine t over 2, dotted with minus 9 sine t, 9 cosine t dt. Okay, so let's factor out. So there's a 9 in both, so we can factor out an 81 over 2. The 2 comes from the first factor. This is the integral 0 to 2 pi. Now we're left with minus sine times minus sine, so that's sine squared, plus cosine squared, so that's 1 dt. So this is equal to 81 over 2 times 2 pi, and this is equal to 81 pi, which is what it should be. Okay, so basically going from this step to this step, you do it however you want to do. Somehow, some way, compute that integral. I sort of did it doing a few steps at once. However you want to do it is fine. But going from that point to that point, you do it. That's you doing math. Okay, and the answer is 81 pi, which is what we know it is. So in other words, the argument that we just made about relating the area to an integral around the boundary of the region at least is true here. And again, if we accept Green's theorem, hopefully you followed my argument. So mathematically, you're convinced, but I just always like to look at an example. It just, for some reason, I just like it a lot. It gives me some amount of joy or satisfaction or something.